Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 159 and 160. We were discussing in the last class the Gibbs Phase Rule. Just the introduction we started. Maybe the introduction, maybe you will say call this introduction. So by way of introduction, we actually uh, wanted to understand what is the degree of freedom, the main issue in the Gibbs Phase Rule. So I'm giving you another example today. That will be easier. So today, so just a draw a line. Today, suppose I give you y is 5x plus 7. We know this is equation of a straight line. Okay. So what is the degree of freedom? F is what? F is I have written anywhere degrees of freedom. This is symbol is F. This I will discuss today, but here f is how much for this straight line? Y is 5x plus 7. This is your y, x, maybe this. This is actually y is 5x plus 7. Here the degree of freedom is how many? How many? See, y and x are two variables. Y, x, two variables, right? X, y, two variables. But degree of freedom is 1. But the degrees of freedom is 1. F is 1. Why? If I fix x, 1 means you fix 1 arbitrarily, independently. So this you remember, independently, very important, or arbitrarily. So fix x, because you have 1 degree of freedom. Why? The justification why f is 1, fix x as said 2. 2 arbitrarily. It 2, well, it can be 3, it can be 4, can be 4.5, etc., etc. So you have a choice on this, but in C you don't have choice on the other. Y will be when x is, suppose you have specified x as 2 independently, freely, arbitrarily, but y must be 5 times 2 plus 7 is 17. It cannot be anything else. Rigidly 17. So this is called dependent. Dependent variable. This is independent. Independent. Independent variable x. Independently, but this is dependently. Both are variables. Why variables? If you change x is 3, say again, uh, uh, again, if x is chosen freely, independently 3 instead of 2, 3. But y, see, y is also changing, see, but dependently. So 5 times 3 plus 7 is 22. It cannot be anything, okay, else, anything else. So both are variables. One is independent variable, x, that is x, and y is dependent variable. So only one independent of this equation, y is 5x plus 7, which represent the straight line. So one freedom is 1. Okay. So fix 1, other is automatically fixed. Okay, it cannot be anything else. 2 can be 3, can be 4, but while say suppose it is 2, then it is corresponding value is 70. So this is dependent. So although two variables are involved, but the degree of freedom is 1. Degree of freedom is 1. Okay, this is degrees of freedom. Degrees of freedom. Okay, there is some okay uh, correlation with these degrees of freedom. One say here in this case, okay, okay, in this see example. So 1 and straight line is also one dimensional. Straight line is one dimensional figure, one dimension. Okay, degree of freedom is 1, corresponds to one dimension. Area is two dimension. Area. This is one dimension. One dimension. And also F is 1. This is area. Cross sectional area, surface area, etc. Area is two dimensions. Two dimension. F will be 2. Example for area, what is the equation? Say x plus 2y plus 3z is 5. So how many? See x, y, z 3. X, y, x variable, y variable, z variables. But you can independently fix 2. Independently. Say x independently. Say anything you like. Say 5. 5. Y, y can also be. In this case, y, unlike this case, here y can be arbitrarily fixed any value. You cannot say if x is 5, y must be this. No. In this case, this is equation of a surface. Equation of a surface. This is equation of a straight line. This is straight line. Equation of a straight line. Straight line or curve. Curve. One dimension. So here y, no compulsion about y. Why I can choose anything. So 3. Then of course these two, f is 2. Degrees of freedom is 2. 2 dimension. Acha 2. Okay. So 2 z will be you cannot. Once these are fixed, z is what? 5 minus x is 5 minus 2y is 2 times 3 divided by 3 from this. 5 minus x minus 2y divided by this. Okay. So what it is? 5 minus x is 5 minus 2y 3. So minus 6 by 3 is minus 2. So this is this is dependent. This f is 2. These are independent variables. Independent variables. Independent variable. And this is your degree of freedom. This is dependent variable. Dependent variable. And it is excluded from degrees of freedom. At one thing, it is not necessary that x and y must be independent and z is dependent, or z is dependent. Or in this simpler case, x is independent, y dependent, not necessary. It can be the converse. Y can be independent. Opposite. Y can be independent, x can be dependent. For example, alternatively, You can start here. Y is 5x plus 7. Repeat this. Repeat this. Okay, this is okay. Repeat this. Here, if independently choose y, y is 17, say, okay, or say, well, 22. Y is 22. Independent. This time it is independent. It can be 23, 24, 5, 6, 7, etc. Independent. Then x is what? X will be y minus 7 by 5 is by 7 by 5 is 3. X is dependent. This time x is dependent, y is independent, but one of them, one. Degrees of freedom is one. One. This is the concept of degrees of freedom, which is the central thing, the cardinal matter of the Gibbs phase rule. This introduction, actually, I am talking of all these things. Okay, so think like this. This is dependent. So it can happen. So exactly number, how many is independent? Your answer is to this. How many degrees of freedom this equation has? Your answer is 1. Which is that? No, not it can be x, can be y. It can be x, can be y. But one of them, that is understanding. One of them. The number is important. The number is actually the degree of freedom, and that is unique. One. But who is this one? Who is this one? It can be x, can be y. This is your concept of initial concept of degrees of freedom, which is the central theme of the Gibbs phase rule. With this introduction, let me move on to the formal discussion of the Gibbs phase rule. Okay, so this I wanted to tell you. Then similarly, here equation of a surface I said. Then equation of a space. Space would be this x, y, z represent the surface. X, y, z, and say another variable n, say for example. So 4 with 4, then that will represent a space. Okay, and that has a 3 degrees of freedom. X, y, z, and n. So this goes on. Actually, there is no end. But this is good enough. This will suffice to give you initial ideas about the degrees of freedom. This is good enough. So I will actually move on to the next thing. So introduction kind of over. Introduction is over. Now take up the derivation. And okay, a few more. Oh, sorry, introduction. Actually, let me remove this. Introduction here. Introduction continued, maybe introduction. Okay. Introduction. I said that is over, but continued. After this, continued actually. Give a star here. Star. Continued. Few things about. But let us formally start actually the few introductory lines about the Gibbs phase rule. Then we will take up the derivation. Very important thing, the derivation of the Gibbs phase rule. Okay. Let us see continued. Continued is this. The Gibbs phase rule applies to both homogeneous and heterogeneous system and heterogeneous systems at equilibrium, at chemical equilibrium. Now note this. So these are the simple examples only. But this note this line. At chemical equilibrium, you have to apply the Gibbs phase rule. So right. Okay. Now the the equilibrium may be this chemical equilibrium. The equilibrium may be in the form of maybe in the form of in the form of reaction equilibrium or phase equilibrium or phase equilibrium or both. This is one couple of lines, introductory lines. In addition, you might be interested what is what are the areas of application, areas of application of the phase rule, areas application of the phase rule. What are the areas of application? Is stability diagrams. Stability diagrams of all types, including the phase diagram, including the phase diagram. This one say this one stability diagrams one, and is second is what? Chemical reactions of all types. Chemical reactions of all types. This, this and this only. This a couple of lines. You underline here chemical equilibrium. It applies to both homogeneous and heterogeneous system. Homogeneous means only gas phase reaction. Under chemical equilibrium, highlight this. Impress upon yourself this word. Phase rule applies to chemical equilibrium. And the equilibrium is what? Phase equilibrium or reaction means chemical reaction equilibrium, or simply phase equilibrium, like say iron solid goes to iron liquid. Or reaction equilibrium is iron solid plus oxygen gas goes to iron oxide, like this. And areas of application is what? The stability diagram. And a kind of stability diagram is phase diagram. But other types of stability diagram will study and will draw ourselves. Very important, stability diagrams. Okay. And then second application is all chemical reactions. Chemical reactions of all types, any chemical reaction. And phase rule requires that, application of phase rule requires that chemical reaction should be in equilibrium. Under equilibrium, then what you will find, this you see, what the Gibbs phase rule gives you, the degrees of freedom. That is very important. The degrees of freedom is how many, and the rest I am actually explain this now. Actually, I will continue talking this. So remove this. This is the phase rule. So with this introduction, next we will take up the derivation. Okay, and derivation you will see derivation of the phase rule. So I think I should remove this now because this is over introductions over. So Gibbs. So next is actually the derivation of the Gibbs phase rule. Derivation. Derivation. The purpose the purpose of this derivation is to arrive at the equation that describes the phase rule, that represents the phase rule. But the purpose is, and what is that? Okay, what does it signify? The purpose is to determine the number of independent variables independent variables called the degrees of freedom of freedom which are required to define the state state of a system at chemical equilibrium. Okay, so so with the help of the degrees of freedom, the expression of which we will derive presently. So we by fixing the say degrees of freedom, number of variables given by the degrees of freedom, we will be able to define the state of the system completely. System at chemical equilibrium. Okay. So start. So this is the objective. This is the to determine the degrees of freedom. So that is to find the expression for the degrees of freedom. Start. So derivation. Consider. So this is the very beginning of the derivation. Consider a heterogeneous system system comprising p number of phases. Comprising p number of phases, namely alpha, beta, gamma, and so on, and C prime number of species. What are they? I, J, K, etc., etc. I, J, K at chemical equilibrium. The number, I can sketch this. What is this? This is a system. You have alpha phase, beta phase, gamma phase, delta phase, etc. Alpha phase, beta phase, gamma phase, so on. Okay, and who are present in this? Okay, this. So what are the species? I, J, K, so on. Similarly, here gamma, say delta here. Delta also contains, this also contains I, J, K, so on. So I, J, so all this. See now, how many this number? I, J, K, L, M, N, C prime. Number of species present in each phase, and alpha, beta, gamma, delta, etc. Epsilon here, okay, imaginary epsilon, okay, phases goes on. How many phases? P number of phases. P, remember, P is the symbol for the number of phases, not pressure, not pressure. Pressure will be lowercase p. I am coming to this, okay. So the number of variables and it is at equilibrium. The system must be at equilibrium. To be eligible to apply the to be eligible for applying the Gibbs phase rule should be equilibrium, at equilibrium. Okay, see, like this. So IJK and so on. So the number of variables required to be specified describe the state of a given mass, a mole of each phase is how many? C prime plus 1. C prime plus 1. Each phase, so consider any one phase, alpha phase. I, J, K, the species present. C prime, since given mass It is not mentioned in books, in, in many books, in some books, I mean many books. The given mass, the phase rule is derived for a given mass of each phase. If it is not, the phase rule would be different. Given mass of each phase. So say alpha. So what is this alpha phase? Who are present? The species I, J, K. This species actually later on I will modify, but later on as component later on, not now. I, J, K are present. So how many species are there? C prime. So C prime moles, C prime number of moles are required to define the state of the system. Remember how do you express a state of the system? State is a function of, remember this, state is a function of temperature, pressure and number of moles. Okay. When you talk a little bit, okay, a little bit actually less loudly. Okay. Okay. So how many is what is this? So remember this. Recall. G prime is a function of G prime is state function. So state is a function of temperature, pressure, N1, N2. So this temperature, pressure, moles. Temperature, pressure, moles. We used to write this. But this is also state function. So we can write state is also state to specify. This is these are actually degrees of freedom. Degrees of freedom. Right hand side. Independent variable. This is a state. This is a state function. So state is also G prime or state is or state is or state is function of temperature, pressure, N1, N2, N3. The three species are there. So and along with moles and along with temperature, pressure. It can be volume, temperature, volume, pressure. These two, just two methods here, and N1, N2, N3. And TP, it can be VT, it can be TV, okay, like this, okay. So these are degrees of freedom. This is degrees of freedom. These are degrees of freedom. DOF. Okay. So question is, so the to specify, required to specify, you have to this is degrees of freedom. You have to specify the temperature of the system, pressure of the system, and moles N1, N2, N3 to specify. That is arbitrarily specified. Independent variable, independently, independent variables. State is a dependent variable. State is dependent on free energy is a dependent variable. G prime. So independent variables. So but specify, independently specify. You have to specify. Then the state of the system is described, is defined. You know the state of the system. How many? 1, 2, 3, 4, 5. Then degree of freedom is 5. This will be. So 5 you specify. Temperature say 500 Kelvin. Pressure say 3 atmosphere. N1 say 2 moles. N2 3 moles. N3 5 moles. Just arbitrarily, but specified. Then it is required to be specified. If you don't specify, the system is not defined. You don't specify. No. These okay, 5. And here you have a choice about this okay, temperature, pressure, it can be volume, temperature, etc. Then all other properties of the system, If you fix this, all other properties of the system can be defined. For example, say if it is gas phase, so what is the volume? PV is nRT. You know pressure, you know temperature, and total moles N1 plus N2 plus N3, you know volume. Temperature, pressure, volume known, mass known, individual mass, total mass, mass known, means moles known. What else then? You make, so since temperature, pressure known, you know the thermal conductivity, you know the heat capacity, you know the surface tension or say viscosity, okay, for liquid gases, okay, all these things, okay. So all properties, electrical conductivity. So, but once you fix this, most of them are dependent on temperature and if necessary pressure. So you fix this. So you have to fix this number. How many? These 5 is more important than who they are. So this is discussed here. It needs to be specified at degree of freedom, that F, if it is F actually, degree of freedom symbol is F. So that's the number of variables given by the degrees of freedom must be specified in order to define the state of the system. System is defined. So I am removing this. So you have understood. So why it is C prime plus, but in this case why it is C prime plus 1? You understand? C, there are C's temperature, pressure. Temperature, pressure, I am sorry, I wrote here temperature, pressure 1, 1, 2, and C prime mass, the C prime plus 2. What is C prime plus 1? Why? Temperature, pressure, and C prime, say N1, N2, N3, C prime number of moles. So C prime plus temperature 1, pressure 1, C prime plus 2, but it is C prime plus 1. Why? You understand, given mass, total mass is given for each phase. I'm talking of each phase. Okay, you one phase you understand, all phases you understand. How to define the state of each phase. Each phase, okay. So why? Because total is known. Say N1, N2, N3. Can you fix 3? Can you independent, all independent? I'm giving a question mark now. I wrote independent, all independent, 3 independent. So C prime independent. Now actually, but question now, when all independent, when given mass, when total mass is given mass, total is given, then can you independently fix? 3? No, 2 only. Because third is given up from this. N1 independent, N2 independent, N3 will be what? From this given value. Okay. N3 will be, this is actually given, is given, N total, say N total. So this is this is given. So N3 will be dependent. These 2 independently fixed, and N3 will be the balance. Total, you know, N total, which is given, the total is say 20. So N3 means 20 minus N1 plus. This will be what? This is dependent. That means 1 less. 1 less. So what it will be? It is not C prime plus 2, but C prime plus 1. This is the message. This is the explanation. Okay. So remove this. I have to remove this. Okay, very good. C prime plus 1. So this is for each phase. Remember, see, follow. Describe the state of given mass of each phase. Each phase, C prime plus 1. Okay. Then how many phases are there? P phases are there. So it will be. So let me write few things. Okay. Here, in what I said here, what I said here is, let me explain this here. Okay, let me give it in writing here. So C prime plus 1. These variables are what? These variables are, as I told you, pressure, pressure is P. Remember, lowercase p, pressure, temperature, T, temperature T, and number of moles, and number of moles, and number of moles of what? How many? C prime. C prime is given mass, total mass of what? How many? C prime, not all of them, one less. C prime minus one species. So, for example, here I am showing you for pressure 1, temperature another, plus C prime minus 1 moles is goes to what? C prime, C prime plus 1, and this is justification of C prime plus 1. This is giving, I have given you here, and these variables C prime, this is actually in bracket, C prime is C prime, number of moles of C plus species. Okay, so this is here we stop. Okay, so C prime plus 1 is explained. Now, for how many phases are there? This for each phase, P phases. So, take up that. If the, and now alternatively, what I am saying, for given mass, I am considering 1 mole. You know, if total mass is 1 mole, then the share of each species is called what? Share of moles of each species will be what? When total is 1, mole fraction. And again, see same thing. Mole fraction, if you express in terms of mole fraction instead of moles, how many mole fractions you can specify? Tell me, for C prime species. C prime minus 1 mole fractions, because for 1 mole fraction, total sum of the moles, sum of all mole fraction is 1. So C prime total is 1. So one of them will be automatically found. Okay, so like say XA is 0.7. Can you fix XB? AB component, binary system, binary. It is C prime, two component, two AB binary system, binary, two pieces are A and B. XA is 0.7 for 1 mole means, so total 1. So what is this? What does it mean in terms of mole fraction? 1 mole. So moles are mole fraction. X is 0.7. XB, can you decide? XB will be automatically. Suppose it is 0.7, it is automatically 1 minus 0.7. This we know. So that means you can choose, when it is 0.7, you choose freely choose 0.3 automatically. So of these two, only one is free, one is independent, other is automatic. If it is 0.6, this will be 0.4. So one less. Okay. So this I am trying next time giving you. So in terms of mole fraction, so finally from moles to mole fraction I am going to actually see by saying that given mass is 1 mole, 1 mole, total is 1 mole, not 4 moles, 5 moles, etc. 1 mole. So this is actually, if the Then also the same thing. Then this C prime plus 1 variables are to be specified to define the state of each phase. So this alternatively, okay, if the mass of if the mass each phase is considered to be 1 mole, you consider phase wise each phase we are discussing. There are p phases. So coming to that later, each phase we are discussing. So each phase mass is considered to be 1 mole. Then the same number of variables, the same number, it remains there. Remove this, one less, one in terms of mole fraction, one less. Okay, because total mole fraction, sum of the mole fraction is 1. So independently one less. So that means same number is coming. Temperature pressure intact and C prime minus 1 mole fraction. So C prime minus 1 plus temperature plus pressure, C prime plus 1. So that if the mass is considered to be 1 mole, the same number of variables, same number of variables. What is that? That is same number means that is C prime plus 1. This C prime plus 1 are required to are required to describe or sometimes describe I say or define the state of each phase in terms of its pressure, temperature, temperature and temperature and composition. Composition, which is this? How do you express the composition? How do you express the composition? By mole fraction. Okay, that is mole fraction of the species. Composition by means mole fractions of the species. So temperature, pressure, moles, they are changed to temperature, pressure, composition. And number is how many for each phase? Per phase, C prime plus 1. And another thing, you remember this? That is why what is the purpose? You have to define the state of the system. You have to define the state of the system. How many variables are required? 1,000? Just so many properties. So many properties: temperature, pressure, volume, mass, then heat capacity, thermal conductivity, then coefficient of expansion, surface tension, refractive index, what not? All properties. No. So do we have to specify? No. You have to specify only a handful of them. That number is called the degrees of freedom. That will be required to, so both are important. Why degree of freedom? That number of variables are required to define the state of the system. That means that is also objective. Define. Your system is fully described by specifying the number of variables given by the degrees of freedom. Yes. So it is so important to find out the degrees of freedom. So you define the system at equilibrium. That is still another important issue. At equilibrium, not non-equilibrium situation. No, no. At equilibrium, there is some. Okay, equilibrium is phase equilibrium, chemical reaction equilibrium. Whole make use of that. That is also playing their role. The system is fully defined. State of the system is defined. This we have studied, but now it is formally we are learning through the Gibbs Phase Rule. This is very nice relation coming. So easily you will get that number. So species, fraction of the species. Okay. Thus for p is, so this is about all one phase. Say alpha, but there are p phases. Thus for p number of phases, p phases. Thus for p phases, the total number of such variables, the total number of such variables, the number, sometimes I write no, number, no, number, often I will write number. So number is short no, number, okay. Total number of such variables, temperature I will write temp, so I wrote somewhere here, okay, or I will write temp, TMP, temp, short for short, composition comp, okay, you take care of this. So total number of such variables, is what? Tell me. Is obviously multiplied by, for each phase, P times C prime plus 1. This is actually the initial development. After so many required. Next issue would be, but actually these are not necessary. These number of variables are not required, don't need to be specified. Not so many. Fewer than this, less than this. Because some of them are mutually dependent. They are not all independent. They should be independently fixed, but they are not independent. Because question of independence comes. Looks like mathematically these are all independent, but not all of them are independent. Because they are bound, they are mutually dependent because of the equilibrium situation. This we will find. So we will exclude that number from this. And the balance, the difference will be the degrees of freedom. This is the whole plan of this derivation. So find out how many of them are dependent, mutually dependent, so that eliminate them, exclude them from this total. In principle, looks like this is the answer. This is the degree of freedom, because these many variables are required to specify the state of the system, which contains p phases, the state of the system, or full system by these number of variables. But the fact is that all of these variables are not mutually independent. There are some mutually dependent. They are to be ignored or discarded. This is the plan. So of this, so this I am actually writing. Of this, however, all variables are not mutually independent. Mutually independent. The number of dependent variables that is the number of restriction number of the number I am writing imposed on the independent choice of the above variables preceding variables is obtained as follows. As follows. So start this. Recall start. So how many are dependent, mutually dependent? Recall. Then that I will subtract from this total. And the result is the degrees of freedom. And the famous phase rule. AP is C minus P plus 2. I will come to this. Slowly, steadily. Okay? Slow but steady. Recall. So this so now concentrate on finding the dependent variables of this total which seem to be independent but actually they are not. There are some dependent there as if hidden there. So find them out, disclose them and subtract them so that a truly independent variables is how many, which will be called the degrees of freedom. And which will be used, are used, which will be used to define the state of the system. Finally, the state of the why they will be good enough, they are capable enough to define the state of the system. When? At equilibrium. At equilibrium bus. This is all full state concept about the Gibbs phase rule. Recall, now we are in the derivation, remember, we are trying to derive that famous rule, mathematical relation F is C minus P plus 2. Okay, this we will try to find out. Okay, so you recall from the second law of thermodynamics. Second law of thermodynamics, the criterion of equilibrium of chemical equilibrium of a system is given by dgpt is 0. dgpt is 0. This means, you remember this, dgpt is 0, the second law. There is another, there is one actually, we see, condition there, that is no non-mechanical work. And since we are dealing with chemical reactions, chemical equilibrium, so there is no question of non-mechanical work, like say, surface work, gravitational work, or say like this, what is called, because this electrochemical work, such things is not there. Then they do, if they are present, then Gibbs phase rule will be distorted. Okay, so they are absent. Their non-mechanical work is absent. Then the second law is purely DGPT is 0. Okay, when there is no non-mechanical work, that we are using, DGPT is 0. This means that the system is under both is under both mechanical and thermal equilibrium. That is the equality of P and T, P for pressure and T for temperature, equality of P and T each among P number of phases, among all phases involved. Among all phases involved, as well as mechanical and thermal equilibrium for constant pressure, constant T means, and obviously Dg is 0 means under chemical equilibrium. So that is the criterion, okay, of equilibrium. So chemical equilibrium of course there, but in addition, constant pressure means pressure is same in all phases. Constant temperature means temperature is same in all phases. So we call it pressure same means mechanical equilibrium. And how many minutes? 1 hour 3 minutes. Okay. Okay. So pressure same equality means mechanical equilibrium. Temperature same means thermal equilibrium. Okay. See, remember this. But P must be same. Okay. Otherwise, mechanical equilibrium will be lost actually. So then, but system has to have a unique pressure and unique temperature. So constant pressure and constant temperature means this. Okay. So that is the equality of pressure and temperature in each phase among all phases. Okay. Okay. See, as hmm, hmm, as well as under chemical equilibrium. So mechanical equilibrium, thermal. Well, one thing I tell you here. So one thing I told you at the beginning, mechanical equilibrium pressure same is pressure of the system and pressure of the surrounding. Same. And thermal equilibrium, temperature of the system and temperature of the surrounding. But here we are talking of system only. So system also, pressure of the system same means pressure is everywhere same, constant, same every point of the system means every phase is covering every phase. And likewise, temperature, same. We cannot say temperature here is 1 and temperature, then what is the temperature of the system? If we one place T1, one phase T1, another T2, still another T3, T4, then what is the temperature of the system? But we say temperature of the system is T, and which is also the surrounding temperature. This we understand. So that means, if you extrapolate a little bit, you have to advance this argument, then you get temperature of the system is in all phases. Same. Likewise, pressure is same. And that is the pressure of the system. And then another thing is this, pressure of the system is same as pressure of the surrounding for mechanical equilibrium. So these are actually very easily understood that, and very easily this logically comes actually. So it stands to reason that okay, pressure among the phases are same and temperature among the phases are same. As well as, so this is about P and T, and then chemical equilibrium. So three equilibrium we are dealing. Three important, three, 1, 2, 3. One, mechanical equilibrium. Two, thermal equilibrium. Chemical equilibrium. Then we will get some equalities, and from which we will get the dependent variables. We'll find them out. So start one by one. Mechanical equilibrium. Okay, so it is better I should write from where. I should write from where actually. I tell you what. Shall I write here? Okay. It is better I write here. The mechanical equilibrium one by one. The mechanical equilibrium dictates that the pressure of all phases are equal. Pressure of all phases are equal. Very good. Very good. No problem. No problem. Are equal. What does it mean? If you write this, means pressure of alpha phase pressure of beta phase, pressure of gamma phase, alpha, beta, gamma phases. P number of phases are there. Capital P, uppercase P. Okay, it goes on. Hence, P minus how many equations you are getting? How many there? Alpha, beta, gamma. How many? P. So how many equations are there? P minus 1 equations. Means equation means restriction. Dependence. Equation means dependence. As I give you at the very beginning example, y is 5x plus 7. Equation y and x bound by equation means both are not free. One is free, another is bound. How many equations? How many free? Or how many bound? Two are there, y and x. One bound. Say y is bound. So how many? One means y and x are two are there. Two minus one is one. Why one? Two minus one. This one is what? Equation. One equation. One equation. So two taken away one is one. Is that dependent? Well, okay, equations. Okay. Now two use it total. So hence p minus one equations or restrictions equations or restriction. These are the restrictions on the choice of on the choice of pressures. Pressures. This means This means that if we fix the value of if we fix the value of P alpha, pressure of alpha independently fixed, arbitrarily fixed. But this equation is there. This equation is there. Can we fix P beta anymore? This has to be satisfied for mechanical equilibrium, constancy of pressure. This has to be satisfied. So supply fix this at arbitrary 2.5 atmosphere. Just arbitrary 2.51. Then it will be. Can I fix it? Can I fix it? No, they have to be 2.5. That means all are not. We consider the pressure of all phases. We have counted here total. P prime. Remember this number. We have counted or each phase. P times. So each phase pressure, each phase. But they are not independent, all independent. One of them are independent. And the remaining are dependent. How many remaining? P number of phases, one independent, P minus 1, P minus equations, P minus 1 restrictions, and P minus 1 dependent or dependent. Same thing, same thing. So this means that if we fix the value of P alpha, the values of P beta, P gamma, P beta, P gamma, and so on, alpha, beta, gamma, up to P, capital, uppercase P, the values of P beta, P gamma are automatically fixed. Automatically fixed and cannot be independently chosen and can't be independently chosen. This is the message. P minus 1. Also, I tell you, number of ways I am telling you. Number of ways. P alpha, see, you fix here. If you fix P alpha, we initially here in this first part, we consider all are independent. When we multiply by P for one phase, C prime plus 1 for P phases multiplied means we consider all are independent. We think about this, all are independent. But no, how is it possible? Because this criteria of mechanical equilibrium is to be satisfied. So one I fix, and that is arbitrary. One I arbitrary fix P alpha, say for example, it can be P beta also. For example, any P gamma maybe. So, but suppose P alpha I fix at, as I told you, 2.5 atmosphere. Then P beta, P gamma window, I have no choice. It has to be. That means they are dependent. But how many are then dependent? How many? Alpha, beta, gamma makes how many? P number of phases. So how many are dependently fixed? P minus 1. One is independent. This is it. Also in other way, in a different way, you see, P minus, how many equations are there here? I'm asking you. Just example. X is Y is Z. The simplest example. Is like this. How many equations are there? If you ask how many equations, how many variables? X, Y, Z. How many equations here? X is Y, y is z. Two equations are there. Not three equations, two equations, two equations. So x is, because 3 minus 1 is 2. P minus 1 is that. So okay, x is y is z. Okay. How many equations are here? Okay, two, two independent equations. Two independent equations. X is y is z. Because x is y is okay, y is z. X is z is meaningless. X is z. This is okay. This is okay. Two, only two. X y z that looks like so. 3 minus 1 is 2. 3 minus 1 is 2. This is the 2. But independently, these are two independent equations. Okay. So 3 minus 1 is 2. 2 is actually okay. Well. These examples actually. P minus 1. Oh, okay. So here also same thing. Okay. No, not this. Not this. This argument is actually replaced this way. I fix x. 3 in this description deals with these relations deal with three variables x, y, z. I fix one x, fixed as 5. Then I have no choice on y and z. I don't have any choice. So okay, restrictions. So how many restrictions are there? Equations. How many equations are there? Oh, okay. Okay, this is very good. No, it's okay. Okay. How many? Yes, I asked you this. How many equations are there? And these are actually restrictions are also this. Is okay. Here as I have already explained you here. Let us come back. Here I fix one p alpha. Others are automatically fixed as I have written here. Others means how many? P minus 1. Automatically we have no independent choice on them. Okay. P minus 1 is justified here. In this way, x is y is z. Also, I wrote something here. This you can say equations available. If equation means restriction, P minus 1 restriction means they are dependent. P minus 1 pressure dependent. Why dependent? Because there are P minus 1 equations. Because there are P minus 1 restrictions. P minus 1 equations, P minus 1 restrictions. So P minus 1 pressures, P minus 1 number of pressures are dependent. Okay, they are not independent. So here also the equations I am trying to counting the equations. How many equations here? When this goes up to where? Alpha, beta, gamma up to p. How many equations are there? Here I said restriction or equations p minus 1. Here similarly how many equations are there? How many equations? How many? In this case, this is very easy. How many equations? Your answer will be how many equations here? Two equations. Okay. 2 means here x, y, z 3. How many equations? 3 minus 1. 2 equations. Equation 2. As a result of which actually 2. Very good. Very good. P minus 1 equation. So equation wise, equation means it is dependence. Equation means dependence. I have no choice. Y is x. Y is x. Means you don't have choice on both. One you fix, other is y is 2x. You fix x 5, y is 10. So don't choice about y and x both. X okay independent choice. For example, y is dependent. So equation because they are tied in an equation. Bound in an equation. Equation means restriction about the independence. So that's why we say x is independent variable, y is dependent variable. It can be opposite also. That I have already said. So, but you consider this. Here, how many equations? Here, p number of equalities. Alpha, beta, gamma, delta, epsilon goes up to p. So p minus 1 equations here. 1, 2, 3. 3 minus 1. 3 minus 1, 2 equations. And equation means 2 are depend. How many equations? 3 minus 1. Because 3 is x, y, z is 3. X, y, z is 3. Total 3. But equations are what? 2. Which are there? You may say, right, this, which are there? If you ask me, what are the equations are? X is y1. Another is y is z. Don't say x is z is another equation, because there is actually coming from this. It has no separate existence. X is y, y is z, or x is z, x is y, x is z. That is possible also. But 2. So 2 equations. How many equations? 2. 2 equations. 2 equations. So of 3, 3 minus 1 is 2 equations. Here also p of p alpha, beta, gamma, delta, p minus 1 equation. Equation means dependent variable, not independent. Two dependent. Here also see 2 dependent. Why? You consider a value of x. Applying here, value of x is what? X is 5 independent. Independent. Then y must be 5, z must be 5. These are dependent. These 2 dependent. Dependent. This is independent, these are dependent. How many? 2. 2 equations. 2 equations are there, so 2 dependent. So this number of equations is number of dependent variables. So you will subtract this at the end to get the difference. Subtract from this difference, and you will get yourself the degrees of freedom. The difference is the degrees of freedom, and that will be your the phase rule. So clear. So here equation wise also you can consider how many equations means. Our common sense also says, oh, 1 I fixed, the remaining p minus 1 automatically fixed. So p minus 1 dependent. We are counting this section dependent ones. Total this, remember, never forget, total this, very simple minded approach, but there are inherent in this consideration, a number of dependents. What is that number? Consider one by one. 3 equilibrium you will apply. Equilibrium gives rise to equalities. Equalities means equations. Equations means dependence, means restriction. So count them. So one by one. So here you get p minus 1. Now you consider thermal equilibrium. I am giving you what is going to come. Thermal equilibrium, there also you get p minus 1. That time this is pressure, that time will be temperature. Then you will consider chemical equilibrium and partial molar free energy, chemical potential, partial molar free energy is same. So again equalities, again equations and dependence and restrictions, dependent variables. We are counting this section dependent variables. So this means the system is here dependent variables or number of restrictions means equations. How many equations? So clearly see here there are p minus 1 equations, and here for example p minus 2 equations, or here coming back p minus 1 equation, p minus 1 automatically fixed. Dependently fixed, automatically fixed. Can I remove this? Can I remove this? I think unnecessary now. So try to follow. Okay, so I was in the right track, but somehow I was actually. So this part is over. So one mechanical equilibrium we have covered. Next we take up. I don't want to remove this top line, but I will remove this. Couple of lines here. This figure let it be there just for some impression and for some. Okay. For some representation. Okay. So next take up. So this because give a star here and give a full stop here chosen. Okay. Oh, yes, no, okay, chosen is this is yeah, okay. Let's take up. So the mechanical equilibrium dictates that. Let us form this star. Which equilibrium next? Thermal equilibrium. The thermal equilibrium dictates that. Similarly, the thermal equilibrium dictates that thermal equilibrium dictates that what the temperatures of all phases are equal. That the temperatures of all phases exactly. Just paraphrase this. This pressure, this temperature. Other is same. All phases are equal. What does it mean? You can write very well. T temperature of the alpha phase is temperature of the beta phase is temperature of the gamma phase and so on up to P phases, and hence P minus 1 hence hence give this hence P minus 1 like this here, like here P minus 1 restrictions are imposed. I am not writing all these things. This part I am not writing. I have explained once. Means I have explained in other cases. Hence, P minus 1 restrictions are imposed. Restriction on the choice of pressures, on the choice of temperatures. Restriction. Write this. Paraphrase this one. So very good. This is the chemical equilibrium. Next, take up thermal over. Next, you will be finally and as well as under chemical equilibrium. Chemical equilibrium gives what equality? This I said. Chemical equilibrium means there should be an equality. Chemical potential equality. These are thermal potential, temperature, pressure is mechanical potential, chemical equilibrium is chemical potential, which is partial molar free energy. Chemical potential. Okay, partial molar free energy. So that is the chemical equilibrium. The chemical equilibrium for the time being, which is which is for the time being considered as the phase equilibrium. I told you chemical equilibrium covers two things: phase equilibrium as well as reaction equilibrium. Both are under the same heading, chemical equilibrium, same purview, chemical equilibrium, which is DGPT, same criterion. DGPT is 0. Delta G, from which delta G is 0. All such things, otherwise same, phase equilibrium or reaction equilibrium. But for the time being, we consider for simplicity phase equilibrium. We will take up, include the chemical reaction equilibrium subsequently. Okay, consider as consider as the phase equilibrium only, as the phase equilibrium only, with the noting here in bracket only, reaction equilibrium to be included later. Don't worry, we will of course include this reaction equilibrium. That will be very important also. Reaction equilibrium will be included later. So no problem. Dictates that which is considered as the phase equilibrium only. eh, or which is for the time being considered as the dictates that the chemical equilibrium dictates that. Is it dictates that? Dictates that? Dictates that? It dictates that. So here chemical equilibrium dictates that. Tell me, dictates that the chemical potential dictates that for the species I. Now on chemical potential there are now there is some difference. Each phase is ijk. You have to take up I first. Chemical potential of I is same. Yeah, in case of temperature pressure, only one temperature. But here you have to consider chemical potential of a species or component. So species chemical potential of I is same in the alpha phase, beta phase, gamma phase, delta phase, all phase, p phases same. Then once count the number restrictions and dependent variables, then take up j, then take up k, and similarly how many there? C prime. Remember C prime was the number of, don't forget that I have removed this. C prime is the number, total number of the species. Okay, so that will take up. This is actually we consider for the case of chemical equilibrium. Okay, so one by one dictates that what for the species I, consider first I, then we will consider letter J and then K, etc., etc. For the species I, this is I, the chemical potential, chemical potential Gi bar, Gi will give you a species Gi. So okay, and the species I, the chemical potential that is the you know you know partial molar free energy. There are various names for chemical potential, partial molar free energy. Okay, mm, four different ways, five different ways you are defined chemical potential. Okay, but since we are considering here to free energy, we will use this. Because I already explained you why free energy. Gibbs free energy is actually the one which is actually very which is useful. Others are pretty academic. Okay, Helmholtz free energy, enthalpy. Okay, like this. Okay, so they are also, but theoretically speaking, they can refer to chemical potential. So Helmholtz free energy can help, enthalpy can, but condition is there. Okay, it is a GI bar is there HI bar enthalpy. What is that? Just I am just returning you to the previous discussion, previous studies, reminding you of that. Okay, to refresh your memory. Del H prime by del NY under constant entropy and pressure. So recall that. So, but anyway, here, so forget about all this. Come back to Gibbs free energy. Chemical, that is the partial molar free energy. That is the partial molar free energy. That is the partial molar free energy means Gibbs free energy. Recall free energy of I, chemical potential of I in all phases are equal. In all phases are equal. Are equal. Here are equal like this. So what is the next line? Okay, one by one. Remember this. Remember this. Okay, this you should not forget actually. No? So write somewhere P prime total variables P prime into C plus 1. total variables means they pretend to be independent variables, but actually we'll see. So total variables. Save this. Save. Here. This we discuss this. Okay. We'll actually collect these numbers, dependent one, collect them together, and then subtract that number from this, and we'll get the degrees of freedom. The Gibbs Phase Rule. And also remember IJK. So C prime species, and what is alpha and P phases. Don't forget, these are all written actually there. C prime species, what are they? P phases, what is this? IJK. IJK. C prime species. Remember IJK. So right here, this you save. And P phases what? Alpha, beta, gamma. So this part is save. Don't remove this. IJK bracket and P phases alpha, beta, gamma. And this is the diagram, and this is they are at equilibrium. Phase rule deals with the equilibrium situation. So is okay where you are. Here all phases are equal. So write this now nicely. No problem. I have saved this one, and this one. Okay. This is very important. So what is this? You write nicely. Like this way, right? GI bar alpha phase is like this. We are choosing chosen species is I first. GI bar, which phase? Beta phase. GI bar, gamma phase. Recall this one. GI bar is actually same in all phases. That is the phase equilibrium. Okay. But is okay. How many? GI bar is okay. Then how many hence like this? Hence P minus 1 restrictions again. And alpha, beta, gamma makes up P number. And these are phases. So P phases. Hence like this. Hence just repeat this. P minus 1 restrictions are imposed, means equations. Equations. Or you may call it equalities, all such things, equations, restrictions imposed. Okay, this one. But you have to, GI bar is not one because we deal with actually temperature, pressure, and composition. So we have to work with composition. So from GI bar to you have to go to the composition. What is this? Remember this. When this is equal, then that is what we write. Or another thermodynamic property is equal at equilibrium. Partial mole of energy, then another activity. Okay, activity AI alpha is AI beta. Gradually we are going to composition. See how is AI, because this count is about temperature, pressure, and composition, mole fraction. Remember, so total for all. So composition gradually through activity now. Here to here is again hence when, but remember GI bar to activity same, GI bar equality to activity equality is when with respect to same standard state. Okay, I will not spend much time. GI bar minus with respect to same standard state. When same standard state is subtracted, then actually same thing you are subtracting. So equality holds, and GI bar minus GI gives RT ln AI, and RT this side RT and other side also RT ln, RT cancel, ln cancel. So AI in the this type of things. Okay, so write that out. So that is when A's are, means activities are. This is sometimes not explained in books. I tell you what, not explained in books. So they just write this, that from this composition directly, or from this to composition, but it's through activity. And why activities are equal, but there is a restriction that should be with respect to same standard set. Where there is activity, there is standard state. No reference of standard state will not signify activity, will not explain activity, will not clarify activity, will not define activity. No, impossible, impossible. Standard state. When AIs are referred to, are considered with respect to, are considered, I remove these lines, these lines also are considered with respect to the same standard state, of I. I. Okay, this actually, or that is continue. Activity is actually, is what we will write xi. Activity is mole fraction Raoult's law. Okay, but remember there is actually this is actually little bit actually involved here. Activity is mole fraction Raoult's law, and deviation from Raoult's law is that we will consider for general purpose xi alpha times gamma I alpha. But here remember that is active. Raoult's law applies when the physical state of the system under consideration is same as the standard state. Okay, and physical state of the standard state. Physical state of the standard state and physical state of the system under study are same. Then you can write Raoult's law, consider Raoult's law, and deviation also. But anyway, you consider this part. I am not actually this can be shown actually related somehow. Already you see this is complicated also. But you have to understand through these equalities. Okay, restrictions are equations means dependent variables. This number very important, hence p1 minus 1 restrictions. So this you will understand. Xi, what do you write? Beta, gamma I, beta, gamma activity coefficient. Is what next is xi gamma phase. Oh, gamma is the activity coefficient. Gamma, triple gamma. Okay, it's okay, no problem. But we understand this what? Write is clearly. Xi is what? Mole fraction of I. Raoult's law reference. Mole fraction of I, the species I, and gamma I is the activity coefficient, right, of I. We consider these mole fractions, but gamma actually now comes to complicate this. But incidentally, gamma again a function of composition. Remember, gamma is a function of composition and temperature. And if you are interested to be, you want to very particular and very meticulous, then pressure, small, weak function of pressure. Gamma is a function of this. So that we mention this, so it will be actually a complicated function of x, but all the same an equation. Here a complicated function of mole fraction of I. And how many? How many is very important. P minus 1 means P minus 1 dependent. That is your gain. That is your concern. Maybe complicated equation, but does not mean actually. But all the same, it gives actually the principle remains the same. That is, you fix one independently, you can fix independently one of them. So please continue. Our gamma I is what? What is this? Now the gamma I, no problem. The gamma is there. Like it is complicating, but no problem. The gamma I being a function of being a function of being a function of xi, mole fraction you know very well, xi and t, and temperature of course. As temperature, this I discussed. Okay, as temperature increases, deviation decreases. gamma decreases, gamma changes and T. And if you want to be very meticulous, very particular about this, is okay. XIT and insignificantly of P of pressure. This is the pressure of P. Not very important, but this deal with temperature, pressure, composition. So equation jumbled up with this temperature, composition, gamma is a function of temperature, temperature coming, but they are jumbled up. Temperature is already there. Okay, no problem. No problem. Equations, dependence. I fix one. I have already fixed one. I could not fix. So I will fix here. Again, temperature comes. The gamma is a function of temperature. Comes. Composition comes. I fix. I fix the temperature. So I don't have control on the others. So this. And in Singapore pressure, don't worry. In Singapore pressure, there are there are how many? See equations? There are how many? Again like this. P1 minus restrictions. Here like P minus 1, P minus 1 equations, restrictions or dependent variables. Then there are P minus 1, write this out. Then there are there are P minus 1 restrictions imposed or written somewhere. P minus 1 restrictions are imposed. P minus 1 restrictions imposed imposed imposed. Okay, is okay. So this is about I. Similarly, but I is not the only species. J, K, L, M, N. How many? C prime. C prime species. So similarly, same deal. Similarly, for the species J present in P phases, all species present in all phases. J here, J here I wrote here, J there, J here I didn't write. Which is present in one phase is present in other phases. This is phase equilibrium. It cannot be violated. Small concentration, that activity same, that too is respect to same standard state, and which is free to represent GI bar is GI bar. Oh, yeah, I am here, alpha, I am being beta, I, beta, and gamma. Then comes activity, but with respect to same standard state comparison, and then okay, this comes okay, activity, this and mole fractions. Then mole fractions, gamma, these are uniform. So mole fractions may not be much. Okay, okay, maybe have varying values. Okay, mole fractions actually will not be same. Okay? Because gamma interferes there. Because this is different discussion, and already I have discussed. Okay, you can yourself find this out. So for the species J present, for the species J present in P phases, they are all present. Present in P phases for the species. P phases, what will write? Similarly, write G J bar alpha is G J bar beta is G J bar gamma, and so on. Hence you write, hence P minus 1 writes, similarly P minus 1 restrictions. Restrictions imposed or imposed. Here right, likewise, similarly, right, likewise, you write here, similarly for, I am writing for the remaining species K, etc. KL for the, similarly for the species K, L say L, I add now K, L, etc., 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 K, L, M, N, O, P, O, like this. So, totaling how many species? Totaling C prime species. Thus, shall I remove this line? This line I am writing, removing this. Thus, so see how many? P minus 1, P minus 1, P minus 1, P minus 1 restriction for I, P minus 1 for J, P minus 1 restriction for J, P minus 1 restriction for K, P minus 1 restriction for L, and so C prime number are there. C prime species. So C prime times P minus 1 restriction total coming from where? From this chemical equilibrium. And you have P minus 1 for thermal and P minus 1 for mechanical pressure first. So P minus, so this. So the right first for chemical equilibrium, write this finally. Just for chemical equilibrium, how many? As I say, P minus 1, P minus P, C prime species, C prime times P minus 1. Just like that. Thus there are C minus 1 restrictions. Okay. Thus there are, just write nicely. Thus there are C prime times P minus 1. Obviously, you clearly see here C prime times P minus restrictions on the choice of mole fractions. On the choice of mole fractions. Mole fractions, see, I have already explained. Gamma can be expressed in terms of mole fraction and temperature also. Okay, so that will be equation complicated. So all mole fractions, say temperature is already fixed, say 1. So it's a mole fraction relation, XI relations in alpha beta. Now one of them is fixed, means remaining are fixed. P minus 1 are automatically fixed. So on the choice of
P minus total for C prime species, C prime times P minus 1 restrictions on the choice of mole fractions, on the independent choice of mole fraction, describing the choice of mole fraction, describing the compositions of describing the compositions of P phases, of P number of phases, p phases involved involved in the equilibrium. Involved in the equilibrium. In the equilibrium. Okay, involved in the equilibrium. Okay, in the equilibrium or equilibria. Equilibria. Over. Okay, this part. This is okay. In equilibrium. Hence, let me write here. Hence, why should I write? Why should I write? I'm giving a star here, double star. This is the first star. Give a double star. Double star. I'm just removing this. I'm getting a here this line. Chemical equilibrium. These expressions are here. So for some reasons I'm not removing this line. So draw a line here. Separate this, and I start from here. This will be very easy now. Hence, double star from this double star. So hence, the total number of restrictions upon the independent then choice upon the independent choice of temperature, pressure, and composition, which is also restrictions means many equations. Restrictions are number of equations are number of restrictions are number of equations and number of dependent variables. They cannot be independently chosen. So that is also the three different ways you can get dependent as different from independent variables. Okay, which which is also the number of dependent. Restriction on independence means dependent variables. I remove this first line. Oh, sorry. Okay. Yes. Anyway, variables, which is also dependent variables, is equal to Tell me how many it is. How many? So P minus 1, I have not removed. P minus 1. Temperature P minus 1. How many P minus 1? 1, 1, 2. And here how many P minus 1? Here C prime P minus 1. So this plus P minus 1 plus P minus 1 means P minus 1. Okay, sir. I'm writing. Equal to, writing you, which is equal to P minus 1 first from temperature, from pressure, P minus 1, plus another P minus 1 from temperature, P minus 1, and from temperature, pressure, then chemical composition, how many? How many here? You did it total? It's simple. There are, here C prime times P minus 1. See. So there are C prime times, okay, not equal, okay, yeah, sorry. C prime times P minus 1, because P minus 1, P minus 1, P minus 1, I, J, K, L, N, P, number of phases, sorry, each case P minus 1 restrictions here, and here, Okay, P minus 1 restrictions, okay, P minus 1 for I, for J, for K, for L, how many species? C prime. So C prime times P minus 1 total, I have written here. C prime times P minus, correct this, C prime times, it's not equal, C prime times P minus 1. So plus C prime times P minus 1, what is that? C prime plus 2 times P minus 1. This is equal to this. These are dependent. They are hidden as if they could not be identified. As if. Now we have identified finally. Okay. So these are out of this, all are not independent. Initially, it seems that they are all independent, but actually there are some dependent part, and their count is how many? So it subtract this from this total. The difference is the phase rule, degree of freedom. Degree of freedom. 1 minute, 1 or 2 minutes more. Difference is the degrees of freedom, and that is the essence. That is the phase rule. That is the phase rule. So let me do this part only today. Okay. So you write this out, variables. Yeah, so hence the right. Remove this all. You have understood? This is over. This is very important. This is very important. Repeat. This is very important. Dependent variables. This is total. This minus this is the degree of freedom. So this. Hence the total number of. Okay. Hence the total number. Oh. Okay. Here continue. So which is also the number of dependent variables is equal to this, which means that continue. Restriction dependent variables is this, which means that the now I am writing the degrees of freedom, the degrees of freedom f or right, or the number of independent variables, or the number Apu is almost independent variables. What is the symbol? This is called f. F is f, okay, or f, f. That the degrees of freedom f is p. Here take this p prime times c plus 1 minus, taking out this c prime plus 2 p minus 1. Okay, do this quickly. P prime c plus p prime minus c prime p c prime, actually. C prime. What is this? How do you get here? C prime, how do you get here? Oh, where it is? C prime. There is no such thing as. Oh yes, C prime, correct, C prime correct. Then what? Oh, I made a mistake here. When I wrote here P prime, total number of variables is what? P into C prime. Well, okay. There is no such thing as P prime. P pieces. P. C prime, not C. C prime. C prime P. So it is P times C prime plus 1. So P times C prime plus 1. No such thing. Okay. So this is a total. Okay. Already given. I saved there. But okay, I mistake. So do this multiplication correctly. P C prime plus P minus P C prime minus plus C prime minus 2P plus 2. Happy? Okay. PC prime cancel, giving you C prime, right nicely, C prime minus P plus 2. Write once more. That is, once more, F is C prime minus P plus 2. This we arrived at where C prime is the number of species. We will go to the number of components next class. From this, how it will be number of components, and that is C. That we will consider next class. So today's class is actually we have satisfactorily reached up to this point, and number of concept of number of component comes with, actually we have to consider number of reaction equilibrium which is actually pending, which I said to be included later on. So number of chemical reaction that will include phase equilibrium we have considered, reaction equilibrium will add, then we will get the concept of the number of component correctly, and then the C will come. Finally, it will be F is C minus P plus 2 the phase rule, but it is not yet. So this is in this form we actually end up today's class. Thank you very much for your patience and for your interest and for your cooperation and everything. Thank you. See you next class. Bye.